And with that, we have hardware security with me. That's so exciting. So who am I? I am Kasey Kiggins. I'm the president of this club. I'm the former head of education. I like orange juice. I play volleyball, and I'm very tired. And my job is hardware security. So what is hardware? Hardware is physical devices. These are like IoT devices. These are modems. These are radios. Basically anything you could kind of touch that like runs some sort of like electrical circuit inside of it can be considered a hardware device. This mic can be considered a hardware device. And then what is hardware security? Hardware security is analyzing the physical aspects of devices and exploiting manufacturer processes or flaws. Hardware devices are, I would not say easy to exploit, but they're a lot easier than most people think, mainly because a lot of devices are not made to be taken apart by manufacturers. They're not expecting people to take them apart. So a lot of them have very common vulnerabilities just because you're not going to replace a router in a building every year, so that router has to exist for 5 to 10 years, and if between those 5 to 10 years there's a vulnerability on it, well, you're just going to deal with it. That's how it goes. There are a lot of manufacturing flaws that are put into this, and I'll just talk about a couple of them today, but yeah. So we'll go over some basic electrical components. Basically, I'm going to talk about like building a device, and then we're going to talk about exploiting a device. So basic electrical components are transistors. They're just like three-way little diodes or little electronical components that take in different resources. So this is like PMOS and NMOS, and there's like MOSFETs, and these are like controlled by logic gates. So if you think of like and or operations that you learn in like discrete math, or maybe you use in your programming, these are controlled that way. So maybe like sending an electrical current that like makes it reach the threshold of 1 will cause the transistor to drain, and maybe making it go to 0, it's just going to cause it to go to source. And that's how those work. Capacitors, those are really cool. Basically, while you have a device on, a capacitor is charging, and it's holding in electrical current in the system. And whenever the device is off, it'll slowly release that electrical current. So if you think in a power outage, and you have like lights, you have your lights on, and then a power outage happens, and your lights slowly start to dim down over a period of time, that's capacitors working to keep the lights on. Inductors work kind of similarly. They also store energy while electrical currents are going through them. But at the end, when the power is cut off, inductors release everything all at once. So it's like a big bright shock. So with the lights analogy, if the power were to go out, all the lights would go super bright for a second and then turn off. And that's kind of like a good way of describing inductors. Both of them have certain places on circuit boards. Capacitors are a lot more likely, and they take up a lot of space on boards. And then resistors, that's to control electrical current that goes across boards. So if you think you have a power source or like a CPU that needs like 3 to like 5 volts of power, but it has to cross a section that needs like a lower amount of power, and it can like damage some of the electrical components, you'll have resistors in there to kind of lower the amount of voltage or the amount of power like going across a circuit board, so that way other components don't get hurt or damaged, I should say. And then diodes, those can be anything from like LEDs, which are like super common, or anything else that doesn't really like kind of fit in these categories. They're sort of a way to just like pass on current or like accept an electrical charge. And then we move on to logic gates. As I said, some of the transistors are made up of logic gates. Logic gates are kind of like the foundation for all circuitry in a way. They're basically what's behind like processing units. You have a bunch of different logic gates like combined together to run like processors and everything. So maybe if you think of like an assembly when you have all the registers and everything, everything moving in and out of a register is moving across a logic gate. So like the bits being flipped 1 then 0, that's going through a series of logic gates like an AND gate, an XOR gate, a NAND gate. And then these are microscopic images of logic gates on circuit boards. They're very, very small and very hard to follow. So like these little dots represent either a connection or an end to something. So this could be like a pin out, or it could just be like the end of like the board being drawn, and they just needed that space for wiring purposes. And then over there, the person who took this photo identified all those gates as like NAND gates, which is pretty cool. Hardware description languages. Hardware description languages makes it easier for us as developers or designers of circuitry to have an easier time designing it. So imagine if you had to design a processor using these pictures, and then you have a bunch of wires everywhere, and you're really confused, and you don't know what to do. Well, you can use hardware description languages to organize that for you in like something similar to like a programming language. There are different types like VHDL, Verilog, and System Verilog. VHDL is really like big in this area, at least. Are really big in this area, specifically because of like government and government contractors, and those devices use a lot of VHDL. And then Verilog is also very common, System Verilog. But the order which this like usually goes is you write hardware description languages, you simulate it, you synthesize it, and then you put it onto an FPGA. You can reverse engineer VHDL. Oh, the L is lowercase. Oh no. You can reverse engineer VHDL and other hardware description languages by like reversing the bit stream. You can decompile it and analyze the routing config bits and interfere with logic or modules. You can also do like chip decapping and microscopic imaging. Microscopic imaging was the thing that's on this page. So people can literally like take pictures of circuit boards and get really, really close up, and then use what they know about how logic gates are supposed to look and identify those gates. And that's really cool because I'll talk about later, but you can actually edit those gates. So you can like take off an AND gate, or you can like change a logic gate to push a bit where you want it to be pushed, like you want it to be a 1 instead of a 0. And then you can get more information off a device. And that's cool. Hardware description languages are mainly just used to help describe what you're doing. It's an easier way of making a processing unit, which these are a couple of the components you can make. You can make a full adder, a decoder, a mux. They're all parts of hardware description languages and things that you can write. Basically, like a CPU or like registers in the CPU are all designed and coded. You can make like processors that are in your computers through VHDL or Verilog or other hardware description languages, and it's pretty cool. So circuit boards. These are cool little circuit boards. That's a circuit diagram before it's made. Circuit boards have a lot of components on them. There are capacitors, there are CPUs, there are ROM chips and flash chips and other things on there. So a lot of the design process goes into fitting everything on a circuit board without having any interference between the two of them. And then also there are other components like GPIO pins, which are like general input and output pins, JTAG pins, or like connectors, and a couple other things on there. And we'll discuss some of them. So a CPU, or a central processing unit, we need those. It's the control unit, fetches instructions from memory and decodes and executes commands. So you think whenever you turn on your laptop, the CPU, as soon as it gets power, it's starting to fetch things from your other components like flash chips or ROM chips to start up your operating system, and any like SSDs or like drives you have on there, it's fetching that, so that way you can access all of the memory and all the things you have saved to your devices. It has an arithmetic logic unit, which is just doing all of the logic across the computer, so making sure that everything's happening correctly. Registers, you guys have seen this in like assembly, if you've ever like altered with different registers. That's controlled by the CPU, and then it has a cache for stored memory, frequent access data, things like that. And then we have ROM chips and flash chips. They're both non-volatile memory, and they both kind of do very similar things. ROM stores permanent data instructions and essentials for device startup and operation. Both of these can store things like the BIOS or anything that needs to be run on like startup. So whenever like your computer maybe like has like password set, if like a manufacturer is creating a device and they want all the passwords to be created like somehow the same, and using like device information like a like serial number or a device identifier, they'll typically have stored on the RAM, like the read-only memory, a file that creates that password. So maybe it's like a Python, or typically they're like C files that are run on startup, and they generate the root password for the device. And those are run with like the ROM chips. There's a couple different other chips. You have programmable ROM, erasable and programmable, and then electronically erasable programmable ROM. Electronically erasable programmable ROM, those chips are a pain to deal with because a lot of them have factors that sometimes if you're trying to figure out what they say, they'll just erase on you, and then you have no access to any of the information. And then flash chips are pretty similar. They store data in memory cells using transistors, and they retain it without needing any power. When you look through like your operating systems and you see like the NAND or the NOR directories, anything in there, those are typically stored on flash chips. Just random access. They have information for the BIOS as well, and then they're erasable and programmable. So if you ever like put a new operating system on your device, this is what's going to hold it. This is what's going to be reflashed with all that information for what it needs to be running the proper system. And this is also if you flash like a system that maybe isn't compatible with the type of like hardware you're running, this chip will like deny it and be like, I can't hold that information. You're silly, and that's what it'll say. Next, we move on to firmware and the operating system. So firmware is stored read-only memory. It's responsible for booting the system and low-level tasks. So it has like all the BIOS setup, like I said. It creates all the users. So a lot of companies in here will have like a regular user, and then like an admin user, and maybe like an admin user. So there'll be like the users for people who are going to connect to the devices. There'll be like maybe the admin of the network, and then there's like a manufacturing admin for if like the person who purchased the device to use it for the network is having problems. So they all have access to the device. It's executed by the processors. And then the operating systems that most hardware devices are running are Linux, just because they're lightweight. If you think of like IoT devices, they're running IoT or any devices that don't have a screen or a keyboard, they're running a headless console or a headless system. And that's basically just means that they don't have any keys or keyboards or display for it to like output to. So these boxes you can only SSH into. That runs like the problem of like me when I'm trying to like get access to this device. Oh, I need an SSH password. Also, SSH has like a whole bunch of different algorithms that like you might need to add when you're trying to connect to these devices. I'll get into that a little bit later. But yeah, most of these devices are running very small versions of Linux that are like very lightweight and are very like not deprecated, but like don't have basically anything on them. And most of these end up being versions of BusyBox. At least most wireless devices run BusyBox for any like troubleshooting needs that they may need. Sometimes they're just like even simpler than some of the BusyBox options. But if you don't know what BusyBox is, it's basically a thing that you can launch on Linux to have like a very small form of like operating system. It's not an operating system in itself. It runs off of like a Unix backend, and it's basically like you have like maybe grep, you have maybe like ls, but then you like can't run any of like the tax or add-ons to the commands. And that makes it really hard when you're trying to use the operating system and navigate through it because you can't like grep for words that you know, such as you're looking for the passwords file and you try to grep for password and grep doesn't exist. So I'll get into it later, but a lot of the times you just make a copy of the operating system to do that. Wrong device. And then the last piece of devices is typically like a user interaction version of it. They'll have websites, they'll have applications. You think like, I think a lot of like smart, what are they called? Like vacuums, like Roombas type of thing. They have like apps now that you can like connect to and like see like the path that your Roomba's going on. A lot of devices for like wireless communications. They'll have like a website that you can like connect to like, kind of like set up your network. They'll have user credentials, so default user credentials that are created, and user manuals. Always get a user manual if you have a device that you want to figure out how it works or you want to reverse engineer and find vulnerabilities on, because the user manual has a lot of good information on there, such as default credentials and other websites that might exist, not to you as a user, but to other people, such as like the manufacturer. And these are a great way to like start whenever you're attacking a device. So you have a device. This is a modem. But what do I do with it? What am I gonna do? So typically, you're going to look at this device and you're going to be like, oh, cool. And you're going to want to like take it apart essentially and just like rip it to pieces. I don't recommend that. I recommend analyzing the packaging first. So most devices can be as inexpensive or as expensive as manufacturers want. And the amount of money that they put into the device is like a clear tell of like kind of the sort of process that you're going to have to go through to connect and like get access to the device. So there's with metal devices that you're looking at, this is typically like transmitters, receivers, any type of modem, satellite devices. Those are going to be either sandcasted or milled. Sandcasting is just so you can get like a more precise layout for your device. And then it's typically put together by like either screws or bonding. Everything is precise and like to the point. So a lot of the devices I've handled have been like, they have like 2 screws and that's it, and everything else is just perfectly fitted together. And that's really important because you don't want any debris, and especially like communication devices that might be like outside or anything, you don't want any debris to be able to like touch the device. And then also devices will have serial numbers on it or device numbers, which could be helpful in the future for maybe, like I said earlier, how passwords are generated, or maybe for other system information to unlock, maybe a user's name something with the device, and that's very helpful. As well as, is the device similar to anything else made by other companies? So hardware is not new, and sometimes it is, but as I said earlier, most devices are going to be in circulation for 5 to 10 years. So a lot of them use the same they use the same processors, they use the same CPUs, a lot of them use the same like designs. Some of them even use like basically the same packaging a lot of the time. So if you like can find if you can find like numbers on there or things that are very similar, you can look up very similar brands. A lot of brands have like the same like parent contracting company that they go to. So a lot of the boards will end up looking the same. And so that's like a very clear tell of like, oh, okay, I've like dealt with something that's similar to this before. So I can perform the same techniques on it. So that's really good. So after you analyze it, you have 2 options. You could either analyze the circuit board and the internals, or you can interact with the user interface platform. Typically, whenever a company is doing hardware research, they buy multiple devices. Because somebody, if they give an intern access to the device, might break it. So the first action that you always go through is you use interacting with the user interface platform. So this is, like I said, reading the user manual. A lot of places use just like admin, admin, user, user. And they also have like default configurations set up. So what I would recommend is checking the website or the application. Most of these are susceptible to code or command injection. And it's really easy to like maybe get access through like SSH or change like the root password or something so you can get onto the device. Why are we talking about websites on the hardware talk? Well, because like I said, you can get root access through like the web interfaces, and then most of the devices that you'll be working with, like I said, are headless. So you're not going to be able to like have like a console, so you'll have to SSH in and you need to find the password. And every time I've gotten access on a hardware device, it is through a poorly made website that has some sort of command injection where I can recreate or change the root password to be root or to be password, and then I can just SSH in there. With SSH, a lot of older systems, and when I say older, I mean like systems that have been like made since like 2012. A lot of those systems are using like deprecated versions of like SSH, so you have to add like key algorithms, this version specifically, and like a bunch of text. It was a lot of Googling on my part to find those. And like they're really, really weird, and like then you'll just get like a bunch of output errors. But it requires, I don't know, a lot of like TAC information to SSH. But once you have like the initial access, it's actually really cool what you can do next. So like I said, most of them are running like Linux, and they don't have commands that you're looking for, such as recursive grep or maybe versions of like netcat or anything like that. So you want to make a copy of the operating system, and For making a copy of the operating system, you make a tar ball, which is essentially you can tar your operating system and then netcat it out to a listener, and then you have a complete copy, and then you can use your own local host to root through any files that are on the device. You can't do that to anything that's in read-only memory. So any like NAND or NOR directories, you're not going to be able to touch. Anything that's run on BIOSes. So like I said earlier, if they're using a certain algorithm to generate the root password, that's going to be in like NAND or NOR. So you're not going to be able to find that, but you'll be able to find other things like website interactions. So maybe there's hidden users on the website that you'll be able to interact with, and you'll be able to change the passwords of that you can find in there, which is super fun and cool. And so there are a lot of like options you can do with this, but yeah, you just like make a tarball and you send it over. If you don't have the ability to use a netcat listener, you can try to send it over with SCP or SSH, but more often than not, if you don't have netcat on your box, you also don't have SCP, which kind of sucks. And I'll talk about later of other ways you can extract the firmware, but that's like the easiest way and the most goated way, because then you don't have to take anything apart. And so that's cool. You also want to look at networking. Most hardware devices that I've looked at are wireless, and a lot of these devices have like IP tables configured to let in any devices that it recognizes, such as any devices that are similar to itself. So if you have, let's say, a satellite, and you have now access to this device, and you know that the default configuration allows anyone of the same like satellite group to be able to communicate with it. If I set up that satellite and connect it to another network of other satellites, I'm able to send traffic to them because they're automatically supposed to recognize me as a trusted device. And that happens with a lot of wireless devices. So looking at those things, maybe opening up a Wireshark capture to see what type of things that it's like, see what type of packets it's sending out, maybe see some of like the wireless communication that it has. Check ports, sometimes they have like random open ports. So maybe like there's a default port left open that you know that you'll be able to like send a payload through. That's something that you can check out, and then you can try it on other devices. Maybe test if you don't like, test without your console access if you're able to get another form of access through using one of the open ports. Navigating your file, I kind of talked pretty much most of this. So searching for file names, you're going to be searching for things like password, you're going to be searching for things maybe like config files, anything that's maybe run on start that's not in ROM. So you're going to be looking for maybe like config files for like the website, you're going to be looking for config files for the typical device, and then you can go in and edit those. If you don't know a password for a device or maybe like an app, and you find, oh, these are a bunch of users and they have like all these hashed passwords, what am I supposed to do? You find a file of passwords and users. Well, the manual typically has the password to the website that you were using originally, and you know what that hash looks like, so you can copy that and then put it in place of the other hash of like an admin user, and now you know the admin user's password because it's just the user password that you already were aware of. And that's pretty cool. You can like find out how the root password was made. I kind of talked about that a little bit. Most passwords are made with device information, so a serial number and a device number. Those are typically like linearly made as well. So like the device number is probably the order in which manufacturing it was made, and serial numbers are typically linked to the date. So most devices have a password function that takes the serial number and takes the device number and runs a funny little script, and then you have the root password to the device. That's really common and has happened multiple times on devices that I've worked on. And that's just like, there you go. You have now the ability to also have the root password of every single device that that company has made, as long as you know the device number and the serial number. And if you have multiple of the same device, then you can tell like, oh, I have device 1, 2, and 3. I bet there's a 4 out there, and then you can have root access to the 4th device. And you can kind of like track those and figure those out through wireless means, but I don't know too much else. What if that doesn't work? Oh no, all of my work, the web interface, I couldn't find anything. You break it, you destroy it, utterly destroyed. Kidding. So first you do part identification. You look at the internals, you find what kind of processors they're using maybe, or what kind of like chips they have. You're gonna look for certain, like you're gonna look for general input and output pins. You're going to be looking for JTAGs. You're going to be looking for UART pins, and all those things I'll talk about in a second. Basically, they're just different points of entry to get into the device. The parts aren't easy to make, like I said, so you're going to definitely be seeing components that other people have seen on the internet. And a big thing that people do is power analysis. So say you're looking at this device and you have no idea what anything on the board is, because maybe like they used like an alcohol wipe and they took away all of the part numbers and identification. Well, the CPU is typically going to be taking most of the power. So you can take a multimeter and drag it across the board and find out where that power is going and kind of find where like the CPU is. You can do that with a couple different other things across the device. A lot of things that you can like identify through like power analysis are input and output pins, which are very helpful. Those are typically like hidden too, because they don't want you to know that they're there. And sometimes they require you like soldering on like a little extra point, or maybe just soldering on like a connection wire for you to actually be able to access those. So what can you do? You can extract the firmware after you take apart the device. One of them is UART shells. So for getting a UART shell, which is basically just the ability to see all the firmware as it's turning on, you would identify TX, RX, and the ground pins. And this is what they kind of look like on like a microcontroller. There'll be little pins that like stick up. If you've ever seen like a Raspberry Pi and they have like the little 3 like pins on the side, that's typically what they are. Sometimes they're labeled, but that's kind of what they look like. And then you can use a serial to USB converter and have a terminal emulator. And then you can just like watch as the device turns on, everything that comes on. And sometimes you'll be able to just like get access from having that connection anyways. So a good example of this is using like, or a good example of doing this is you have a device and you use like the UART of a Raspberry Pi. You have like a little connection. So you connect your device to a Raspberry Pi, and then you connect your Raspberry Pi to a converter to your local machine. And then you're able to like see when you turn on the device, like BIOS starting, all of these files coming in, all of this coming in, all of the registers going by. And then sometimes you're able to just like pop a shell. A lot of these aren't password protected sometimes, like IoT devices. This is a regular attack to use against IoT devices. They don't have like a password protection. So you can just like get a shell on an IoT device and then mess around with some of its configurations, maybe find a cool vulnerability. And from there, you can like make a copy of the file system. You can extract the firmware onto your device. You can do a whole bunch of different things. Those are like the big ones. You can also physically solder or desolder chips off a device. That's really hard, guys. You get, basically, for this process, you get a big piece of heat protectant film. You cut a square out to where you want the piece to be. So for this, I would have a big piece across this and say I want to take off like the CPU. I'd cut a square out where the CPU is, and I'd hit it with a heat gun, and I'd spray it with the heat gun. I'd hold the heat gun a little bit away, and I'd heat it up, and I get this little pick that has a suction cup on the end, and I tap it. And if it's not coming off, I hit it again with the heat gun. I let it go a little bit, and then I tap it. And if it's still not coming off, hit it again with the heat gun. Let it go on a bit. Touch the board to make sure it's not getting too hot, even though there's heat protectant on it. And then eventually, you take your little suction cup, you stick it, and you're able to lift off the little chip that you're trying to read. And that's a lot of work. How these things are soldered on are like perfect little like ball pins and like little bits of solder. And so whenever you take something off the board, you immediately want to like clean it and get rid of all of the old solder and clean both sides of the chip to make sure that there's no solder that's like going in between like the little pins on either the chip or the board. And then what you can do is you can use this chip reader. I've seen one like this before. I've seen a couple, actually. These are things that you could either like buy in like the United States for like $200 to $300, or you could buy like a Chinese knockoff for like $40, $50, and like all of the extensions to read a bunch of different size chips. But basically how this works is you pick what array it is, which could be like, just an example, like a 16 by 16 array. And you're like, this is a 16 by 16 array chip. And then you select the size for it, and then you press it down onto this reader, and you plug it in, and you run a reader software. And basically, what the chip will do or what the reader will do is that it will spit out all of the contents of what that chip has. So typically this will happen to like a flash chip or a RAM chip, something that's holding firmware, and it'll like identify what type of firmware it is. It'll identify what type of like device slash chip you're using if you don't already know that, and it'll spit out all of the contents, and then you're able to put that into a file, and then you have like a bin file of the firmware of a device. Why don't people do this more often? Well, one, because it's annoying to take off the chip, and then two, it's really hard to put the chip back on. Like I said, 16 by 16 array, very meticulously placed. If you take this off, hopefully you have a second device, because this is definitely not going on correctly. And if it does, it's probably not going to work, because it's really hard to put back on. It's really hard to solder back on. And so you just kind of, you're in no man's land for that. So like I said earlier, if you're going to do this and solder pieces off of something that you're like, oh, I want to use this later, or I definitely like want to continue working on this device, have two of them. That's like the best thing I can offer. Or just be like goated with the sauce on resoldering. And then another way to like physically extract like firmware, you can use JTAG and SW interfaces. These are designed for testing and debugging on like the chip level, so they have a lot of access. So they provide access to the CPU, and to like extract firmware, you can identify the JTAG connections. JTAGs are typically hidden on devices, so you have to do a couple like power analysis tricks to kind of like find them, mainly because they are debugging pins, so people don't want you to easily find them. That's so mean of them. And then you want to memory map the chip, so that would be like figuring out what registers are happening once you get like a connection, and figuring out how the chip is kind of like working, and then you can extract the contents from memory. Right here, this is a JTAG reader slash like adapter, and you're connected to it. There's a bunch of different tools that you can use for it, and basically you read the memory, and then you can flash it to like a directory essentially, and this is like the address of where the memory starts, and then you flash it and everything, and then it's done, and there you go. You have a copy of the firmware, which is pretty cool. More about JTAG, you can interact with it with a couple things. I think it's like there's like an open SGR, it might be called. I'm not entirely sure. But there's also URJTAG, which allows users to interact with the device and read and write assembly instructions. So say you're running this device and your laptop's connected to it, and you're wanting to test out like how it works whenever you edit or modify certain components of it. What you can do is you can edit the assembly as it's running. So I power it on, I have it going, and you know what? In like 2 seconds, whenever it powers on, this instruction is always going to be like raised, or this instruction is always going to be like this thing, you know? And I want to see what happens when I make this instruction, this address. You can do that, and you can have it skip over making a password function, or you can put in your own password function. So if maybe you don't know how to create the root password of the device, what you can do is when they get to making the root password of the device, by you watching the firmware as it executes, you can skip that instruction for it making a device password. And then the device doesn't have a password, and then you can just SSH in, or you can just get a shell through some of the other methods that we talked about, which is really cool. You can also like execute other things to happen if you want it to like ignore other things, or you just like want to like brick it. You can write in like a certain command, like say you want to give like a broken device to somebody. I don't know why you would do that, but if you wanted to, you could add in like the wrong address for it to map to, and then like the memory's all scrambled, and then you can't use it. But those are really like the main things you're going to be using that for. And then these are some more like common attacks that you might like hear of. You can hear about like side channel attacks, which is a security exploit that attempts to like extract data and like secrets from a chip or a system through like measuring or analyzing various like physical parameters. And basically it's like supplying current, execution time, and like electromagnetic forces to the boards. It doesn't like target a program or like code directly. So some of these, some that I can like speak to are like timing attacks. All devices have this thing called a watchdog timer, and it's basically the timer that keeps everything on the device synchronized. And what you can do is you can overload that timer and cause it to skip. And sometimes in devices, if they're not properly made, a skip in the watchdog timer can just like shoot you out a shell sometimes. basically what you do is you kind of just like overload the timer with like power, and it can like create like a jump in the clock cycle. And when you like have that jump, you're able to like maybe execute a command that you wouldn't already be able to execute, which is really cool. So that's like a timing attack, is messing with like the timing. There's also like power analysis and differential power analysis. You can provide different levels of power varying across the board to make different processes happen at different times. So say I'm giving like a constant of like 12 volts to a board, and when it's starting up, it's like interacting like with a process that I don't want it to do. I'll drop the power before that like process happens, or I'll drop it while it's happening so the process can't complete, and then I'll hype it up after it's done, and so that it'll like skip the process. Sometimes that happens. Sometimes it's just like it then waits for the power to come back up and it restarts. That's boring. And then super power analysis I've already talked about, just like going across the board with like a multimeter to like discover devices and a couple other things like that. There's like fault injection, which is like trying to deliberately create errors. So voltage glitching, that's something that I kind of like explained. You can force like voltage glitches across the board by like editing some of like the logic, what are they called? Logic gates on the board. You can also cause voltage glitching by like maybe supplying it with like your own like power source and editing the amount of voltage that you give across the board. Clock glitching is very similar. You could like stop the clock on the device, like disconnect some of the clock pieces. Like if it has like a different clock besides the watchdog timer on the device, you could take that out. And then you could do like electromagnetic ones, which I don't know too much about those attacks, but those are really cool. It's just forcing like a glitch by giving it like putting it under stress and causing it to have problems. Yeah. This is my favorite type of like hardware attack. This is a hardware Trojan. And it's basically when you modify an integrated circuit, like a PCB or a printed circuit board, to cause information leaks and like denial of service like attacks, you can create like a hardware backdoor on a device. And that's just like so cool. And like, it's like crazy. And it's really hard to do. I've never done it, but I read a lot about it, and it was cool. Basically, it happens on like the circuit board level, and it's with like logic gates and like the layouts. And basically, what you do is you can like edit the logic gates to transfer like incorrect signals, or like a 1 instead of a 0, or like that's basically what logic gates are doing, a 1 or a 0. And you can force like a 1 or you can force a 0, and it will cause it to like leak some like hardware description language or some firmware. And it can like leak access to the device, which is really cool. So you can like send in a payload while it's running. Some devices have these like built in by like having like hidden front doors, which is so like, say you have like, I don't know, maybe like your router's broken and like you take it into like a shop, like the manufacturer, and you're like, hey, Cisco, fix my router. Sometimes they'll like use like these like hidden front doors to access the device and be like, oh, this is like the problem that you had because maybe you like reset all the passwords. I don't know. But that's like a thing that they'll have hidden, and you can like find those, and that's just like embedded in the logic gates. So if you're like analyzing a device and you find one of those, you just like have like Trojan access, which is really cool. The goal is like you can is to easily modify like certain input or output pins or cause like a bit flip. And that's just like really cool. And sometimes you have to like reverse engineer like hardware description languages, which is really difficult, but it's fun and cool. And that is it. That's my slide. Oh, I'm a little early. But if you guys have questions, I'll answer them. Does anybody have fun questions? Yeah, Anthony? Mm-hmm. If you want to try these things, how would you acquire these devices? Well, some things that I like to recommend: have a really cool boss who's getting rid of things. That's what I did, and that's very helpful. You can go to GovDeals and buy a bunch of one device like very cheaply, and then you could just like desolder things off of that device. If you wanted to go into like hardware hacking on your own, I would recommend like starting with a router, or starting with maybe something that has like wireless signals, like a modem or something, and taking that apart. Those are really cool because typically they have a user interface, so you can like apply like your web knowledge. They have console access in the form of like SSHing in. You have the default credentials through like a user manual. Those are very nice. And then if you want, you can desolder items off, and you can get a chip reader and use those. For things to use to like hardware reverse engineer. If you want to practice soldering, the shed has a like soldering lab, like a circuit lab, where you can build your own printed circuit boards and like make your own like little devices there. So that could be something fun. You do have to like go through an online class through the shed to like be allowed to do that. RITSEC also has a soldering iron, and if we had proper ventilation, that would totally be part of the demos, is to solder something. But we don't have proper ventilation, so that's sad. So either of those like really works. Yes, Will. Mm-hmm. Yes, Will said we have a research hardware inventory and research grants if you need to buy some. Does anybody have, yes, question? Mm-hmm. How does reverse engineering hardware description languages go? It's basically like a bit stream, and you have to identify things that are like frequently happening inside the bit stream. So you see like you have a bit stream and then you have to like categorize it, and you're like, okay, these look like ands and ors, and these look like these processing units, and then you kind of like compartmentalize how they work. It's kind of like having like a disassembler, but a little bit harder, because instead of like assembly instructions, you have like just like ones and zeros. But a lot of the time, like an AND gate or an OR gate, those have like similar things across like the board, so you can like use what you already know of, like this is always going to be an AND instruction, this is always going to be an OR, to like kind of like figure out how it's going to go. Mm-hmm. Any other questions? Yes, Anthony? Have I done most of these on cool stuff? Yeah, I've done a lot of this stuff. I've never reverse engineered a hardware description language. I watched like 4 videos on it though over the summer, and that was cool. But yeah, I've desoldered circuit board components. I've used a chip reader. I've most of like the things that I talked about, I've actually done. That's why I was able to talk about them. I took apart an IoT device in the summer, and I just like figured out how like that worked kind of. And my boss helped me with a couple other things over winter break. So that's like pretty cool. A lot of the stuff I would say, like you could just like watch videos about people taking apart things and like showing you how they work, and it's so cool. Yes, Will Dandrid. Is hardware mentorship ever coming back? Hopefully. I've been very busy with my role as president of RITSEC, but I hope next semester, I already actually made like a lesson plan. It's gonna be like VRig style. This is like leaks. Hopefully it'll be like VRig style, where we just like have a device and we just like mess with it. But it'd either be mentorship or an interest group program. But that'd be cool. Any other questions? Okay, awesome. So that was my talk. Dan is in a meeting. The demos this week are posted. 2 are by Dan and 1 are by me, I think. And they'll be fun, cool, and swag. Oh, AB. I'm sorry, I didn't see him. Yeah. AB gets to explain them. This is also the last regular general meeting of the semester. This is the last education talk of the semester, guys.